I'm very happy to chair Alessandro. For him, I changed room from room A to room B because he's talking about something I used or tried to use in 2 of my papers, and I never really understood it. So hopefully after the course my future papers will improve and I have someone to cite when doing so. So Alessandro is a PhD student at the University of Genoa, and he will talk about Monte Carlo algorithms for Bayesian inverse problems for 2 hours. So I guess we will make a break in the middle.
Yeah.
And you have the stage.
Okay. Thank you very much for the introduction, and I hope you will enjoy the presentation. Okay. Thank you. I just start a little bit saying what. So now the microphone is on, but okay. Just talk a little bit about what an inverse problem is, but I think that everyone knows it. So we have an operator that works between 2 Hilbert spaces. That is the forward operator. And then we measure something, the data, and we want to reconstruct the configurations of the unknown that are x that generated the signal, the measurement that we measure. And then here I just introduced some additive noise that is the one that we will focus on. And of course, in the analytical approach, that is the most common one and the widely used, okay, so it's useless the microphone. In the analytical approach, what we commonly do is something like a L2 regularization or some other stuff like LT or L variable P regularization, and something like least square. So we are looking for the configurations of the unknown that best fits the data. This is what we do, and we just use different metrics and different weights in order, for example, in the economic regularization, for finding our solution. But we are not looking for that, we are not looking at that. We would like to focus on a Bayesian approach that is something different. We introduced some random variables whose realization are the one that generated the data. So the problem from little y equal f of little x and so on becomes a relationship between random variables. Here x and y and n represents random variables. And each one has its own distribution that are p of x, p of n, and p of y. Why there is a difference between capital P and little p? Because the distribution is a measure. We used to work with densities. So when I say the Gaussian distribution, you just think about e to the power of something. But e to the power of something is that one, is the density with respect to the Lebesgue measure. If we want to generalize this approach, it's better to work and to use distributions, so measures. And each distribution could have a different density with respect to different measures, and due to the Radon-Nicotine theorem. Okay. And this is a common notation in probability theory or in Bayesian theory. When I write a p of d something, it's like writing down dp. It's a measure. Okay, so we can write down the Bias theorem, assuming just that the likelihood, so the density of that tells us the probability of having measured y, given some configuration of the unknown x, as the common Bias theorem may be a little different, because here we are saying that the measure that gives us the posterior is nothing but the product of the likelihood times the prior. But this identity has to be seen as an integral identity. So this one makes sense only when we consider integral values with respect to x. I'm using a common notation in probability theory, but I know that it's a little bit tricky maybe at the start. And at the denominator here we have the so-called normalizing constant, and it's not so important in our purposes now. Okay, and the prior distribution is the distribution of the unknown, and this distribution, so this measure, embodies what we know about the unknown and all the prior information. Okay, and why would we prefer a Bayesian approach? So looking at the distribution of the unknown given the data instead of an analytical approach that gives us the solution with some different metrics, minimizing some functionals, because of the so-called uncertainty in quantification. With a Bayesian approach, the posterior distribution that we would like to reconstruct has different peaks and could be picked more or less depending on our uncertainty for the solution, for the given solution. So the variance. Okay, but if we don't want to use a full Bayesian approach, so when we would like to reconstruct the entire posterior, but we would only use some estimators, we can use the so-called, the most common one, the maximum likelihood and maximum a posteriori, that are nothing but a generalization of the L2 regularization and least squares. Why? Because the maximum likelihood, so the configuration of the unknown that maximize the probability of having measured y. So we are using some configurations and we are looking for the one that best fit the data. So here we are fitting the data. In the case of a Gaussian noise, and I recall you that we are considering additive noise. So here it is a Gaussian additive noise. And in the case of a Gaussian prior for the x, the maximum likelihood turns out to be the least square solution. Why? Because in the case of a additive noise, I just maybe forgot to say that, in the case of an additive noise, the distribution of the likelihood, so the distribution of the data given some configurations, is a translation of the distribution of the noise. Because if I give you the data, the unknown, sorry, the distribution of the data is the translation of the distribution of the noise. So if we consider a Gaussian noise, the distribution of the likelihood, so that one, is the translation of the distribution of the noise, centered in the data. Okay. And so the maximum of a Gaussian distribution is the minimum of the minus log likelihood. And this is the exponent of the Gaussian distribution. Okay. So this one is shows that a maximum likelihood can be seen as the least square solution in a Bayesian approach, probabilistic approach. And the maximum a posteriori, so the configuration of the unknown that best fit the data depending on our prior choices, because the posterior is the product of the likelihood times the prior. So the one that maximizes the posterior in the case of Gaussian noise and Gaussian prior is again the something that we know, that is the L2 regularization with a specific regularizing parameter. This is lambda. And it's the ratio of the variances of the two parameters. But here, what we find in both cases, for example, in that example, is 1 point. We are looking only at 1 point. If we use the maximum a posteriori, or the maximum likelihood forward, we find only the highest peak of the posterior. But the posterior could be multimodal. We can have, like here, another peak. And I'm interested in that because maybe the noise could shift the data, and I would like to know the distribution of the unknown. So bye.
Can you explain better the difference between the maximum a posteriori and the...
Yes. These two estimators are the first one, the maximum likelihood. Okay. With the maximum likelihood, you are looking at the maximum of the distribution, that one, the likelihood, the distribution of the data given the unknown. So you are looking at only the configurations that maximize your expectations, your expectative, le tue aspettative. Sorry. You are not looking at on what you know a priori, so about your knowledge on the unknown. And this is the maximum likelihood. So you are looking at the configuration that best fit the data, nothing else. While in the maximum a posteriori, you are looking at the maximum of that product. So you are embodying the model with your prior knowledge. No.
Thanks.
You're welcome. Okay, so now I'm introducing importance sampling. What is importance sampling? No, not now. Just talk a little bit about what Monte Carlo methods are. Monte Carlo methods are algorithm that allows us to approximate some quantities, integral quantities of functions with respect to some measure. So we have an integral of a function, integrable function with respect to that measure, but this is just, we are saying that this integral converges. And we want to approximate it, this integral. This is the expectation of phi with respect to p. But commonly we use in probability theory the notation of p of phi. But this is the expectation of phi using the measure p. That is the measure that is inducted by the random variable x, the distribution of x. Okay, so how can we get an approximation of p of phi, so that integral with a Monte Carlo method using the law of large numbers? In fact, if we are able to sample multiple times, a lot of times, random variables distributed as p, so as the measure of the integral, then we are able to approximate in almost surely the integral. Of course, we need that our samples are independent and also distributed as p. So now the problem is just I sample xn a lot of times, then I have to be able to evaluate phi of something, but I'm supposed to be able to do it, and then I'm sure, thanks to the strong law of large numbers, that this sum converges almost surely with respect to p. So almost surely it means up to sets with zero measure, with zero measure with respect to the measure p, because we are considering integrals with respect to p, and then we have this this theorem, and we have converged. There is nothing so terrible, so we can use the so-called direct sampling, or something similar. It has many names, but we sample IID random variables, then we evaluate the approximation of the integral, and then we are sure that this converges. What is the problem? Why I have to talk, I hope, less than 2 hours for explaining why we have to introduce this Monte Carlo algorithm? Because we are not able to sample from the posterior distribution. We are not able to sample from each distribution that we want to. And so we have to introduce some other ways in order to get independent samples from such a measure. And what we are looking at are importance sampling, Metropolis Hastings, that is a particular Markov chain Monte Carlo, and a little bit we will talk about sequential Monte Carlo. That is a fusion of the 2 previous ones. Okay, so the main idea is I'm not able to sample from P. I would like to introduce some other measure where I am able to sample from, and then I'll do something in order to fill the gap between these 2 measures. We introduce a dominant measure with respect to P, so if we are thinking about densities, so about functions, a function that has a bigger support compared to the one of P. These notations maybe also can be seen as P is absolutely continuous with respect to M, or M dominates P. And we are able to sample from M. That is called importance distribution. So we can change the measure of our integral. We just practice as change of measure. And we have to introduce the so-called Radon-Nicotine derivative. We are just changing the measure. So we start with our first integral. We change the measure, introducing this M. And then, due to the fact that I'm changing the measure, I have to introduce the Radon-Nicotine derivative that are the weight that fills the gap between P and M. So, what are we looking at now? I know that if I am able to sample from P, then the sum of phi of x with x that is sampled from P, if I do a lot, then I converge to that integral. But here we have the same thing with M, and I'm supposed to be able to sample from M. So I just sample from M, and then I evaluate phi w. Okay? And so, if I sample from M multiple times, I know that this product, the sum of that product, will converge to our integral.
You don't know the weights.
Yeah, I know the weight. Okay, sorry, one moment. I know that this notation is terrible because at first I hated this, but because here we have the ratio between 2 measures, while here this is a function, and the evaluation of that function means that the integral. This is the common Radon-Nicotine theorem. The integral of W with respect to the measure M is the same as measuring with P. Okay, but I know this ratio because I suppose that the 2 measures are P is absolutely continuous with respect to M. So if P admits a density with respect to the Lebesgue measure, also M has a density with respect to the Lebesgue measure. So this means that here I just have the ratio between the density of P and the density of M. No.
You know the ratio, but not P.
Yeah. But I'm able to evaluate P at each time. For example, if I tell you, just take some samples from the sum of 10 Gaussian times a Poisson. Are you able to do it? No, but you are able to evaluate it. No. So you're not sure that I can evaluate P at each time.
You say that you don't know how to evaluate P.
I don't know how to sample from P.
Okay.
But I'm able to evaluate P because I know P.
Okay.
I know my model,
Okay.
and the measure gives us the model. But I don't know how to get some histograms that are distributed as P. And otherwise, I'm able to construct some histograms that are distributed as M.
But it is always possible to find M which dominates P? Because if you don't know P...
Yeah, no. The fact is that you can find a measure that dominates another one. I'm thinking about the Lebesgue word. So if we have the Lebesgue measure and you have such a measure, you can take the maximum of P, and then you can get a measure that is flat. Yeah. And this has the support that is bigger, and you are sure. The problem is that if the two measures are too different, this ratio can become or very, very small or very, very big. And you don't want to have weights that are too different from each other because of the convergence or numerical problems. But I think that I don't know if you take a measure and another one, if you take a measure, you're always able to take a measure that is absolutely continuous with respect to that. But in the Lebesgue world, I think yes. In the whole world, I don't really know it. If someone knows it, just take it. Aside. Okay. But the idea is very simple. Okay. Okay. Sometimes, as I told you when I explained the Bias Theorem, we don't really know the distribution, but we know something that is proportional to this distribution. In fact, I was saying a little bit earlier that there is a normalizing constant that we don't care about when we use a Bias Theorem. That is the distribution of the data. And so we just know something that is proportional up to a normalizing constant, constant L. So we just introduce the same weight because we are changing the measure. The only difference is that PU doesn't sum to 1, it sums to L. So this is not a probability measure, but is always a suitable measure for our integral. So we introduce the weights that are the same. The only difference is that we just normalize the weights in order to have something that sums to 1. And this, that is called the self-normalized importance sampling, is so useful because it also gives us the possibility to evaluate the normalizing constant. Why? Because if we take the sum of the weights, that sum sums and converges to m of w. So the integral of w with respect to the new measure, the importance measure that we introduced. But this, due to the definition, is pu of x. It's the integral over the whole space of the previous measure. Because w is this ratio. If you do the integral, m of x dies. And then we get pu of x. It's L. So our normalizing constant. And for once of you know about that stuff, the normalizing constant in inference is useful when you want to compare different models, because this is called evidence. So if I use a model and I get a normalizing constant, and I use another model, and I get another normalizing constant, the one that has the bigger normalizing constant is the more evident model, so the model that is more suitable for our problem. But we don't focus on that. Okay, so roughly speaking about convergence, we said that due to the strong law over large numbers, we know that our approximation Pn, so the sum with respect to the product phi times the weights, converges almost surely, P, I forgot to write it, to our integral. And what about other convergence? We introduce, okay. What about other convergence? So the central limit theorem, so we know the convergence in law. We know that Pn is unbiased due to the strong law of large numbers, so the mean of Pn is P of phi. And we also know, due to the fact that this is unbiased, that the mean square error is the variance of the product of the two. And this means that the central limit theorem tells us that the difference between our approximation and the true value of the integral converges in law to a normal distribution that is centered in 0 with a known variance, that is the variance under M, so the importance measure of the product of phi and W. But the focus is, the strong law over large numbers tells us that we are converging in mean, but not in variance. We don't know if the weights and our samples are really concentrating in the true point of our posterior, in the peaks. Here, with the strong law over large numbers, we only know that if we do the mean, we get the right solution. For example, I have one point, one sample that is centered in 0 with a huge weight, and then thousands and thousands of samples that are far from the higher probability region for P with low weights. This, if I do the average, I get the true solution, but I have a huge difference in the variance of the weights. There is one sample with a huge weight and a lot of samples with small weights. And this is not a good stuff. We want to converge also in variance, so that the variance of the weights is something not too different between different samples. And this is what we would like to do. We are really converging also in variance. So we would like to bound that variance. If this is small, this means that our samples are really distributed in low SP. Okay, so we would like to have a small variance of that product, and of course, if we consider bounded function, this means that the weight has to have a small variance. So we don't want that the weights are, for example, one with a high weight and the other one with a small weight. Okay. We saw the almost sure convergence. We saw the convergence in law. I think that it's called in that way. Convergenza in legge, convergence in law. In distribution, maybe. No, vabbè. In law, okay. But also, important sampling can be seen as a construction of a sequence of measures that weakly converge to the measure given by our integral. So converging to the measure that here there was written P. This is just the definition of the weakly convergence. So important sampling is something like I'm constructing a sequence of measures that weakly converge to P. Why? I just recap what means weakly converge to something. We say that a sequence of measures weakly converges to a fixed measure mu if all these integrals, so if the integral of all bounded functions with respect to mu n converge to the integral with respect to mu. So we can say we have the limit outside the integral when we put it inside, something like that. So if we define a measure Pn, just remember that Pn of phi is different from Pn of the x. Pn of phi is an integral, is a number. Pn of the x is a measure. And the difference is that it's not the sum of the weights, it's sum of the weights with this delta. Okay? So if we define this measure, then importance sampling is saying that this Pn are converging weakly to the target measure P. Okay. And so this is what I just said. But so importance sampling gives us weighted samples. We have some particles, and then we have each one has its own weight. And of course, they are distributed according to m instead of p, because we are not able to sample from p. How can we evaluate the quality of this sample? We said that the variance of the weight is something important, because due to the central limit theorem, we want a variance convergence. And we introduce the so-called effective sample size. This is something related with the empirical variance of the weights. So this is a good value to look at when we want to see if our sample is good. This is nothing but a ratio between the sum of the squares of our weights, and this is why it's related with the variance of the weights. This belongs to 1n. N is the number of our samples. And this tells us the number of independent samples from P. So if the ESS is, for example, free, we know that from n samples, there are 3 samples that comes directly independently from P, even if we are sampling from M. Okay? It can be interpreted like that. This is not the true definition, but it's useful to see it like that. Why? Because if we think that k weights are equal 1 and the others are equal 0, then the ESS is equal to k. And what does it mean that a weight is equal 1? I'm just going back to the definition a little bit. Okay, well, if the weight is equal 1, this means that P and M are the same. So if I get a weight that is equal to 1, it means that I'm sampling from P. Okay. And of course, this is related with the variance of the weights. And of course, the higher the better, because it means that we have, if the ESS is n, this means that we are currently sampling from P. Okay.
The weights can be different from 0 and 1, can be 1 half.
Yeah. But in fact, this is just an intuition of what the ESS is. For example, sometimes the ESS is good if it's higher than half of the samples.
And what do you say about the independence before? You say something about...
Yeah, because if in that case, where just take the when we have k weights that are 1 and the others that are 0, this means that we have k independent samples from P. Okay? just because if the weight is 1, this means that we are sampling from P. And of course, these are, I didn't note it, but these are all independent, because I'm supposed to be able to sample independently from M. But if the weight is 1, this means that I'm sampling from P. So, which are the pros and the cons? Of course, this algorithm is parallelizable, so we can work with different machines and then put together the results. For example, here I just run 3 times with 100 samples at each time, and then we get the histogram that is nothing but the superposition of the 3 with the 300 of samples. Why? Because they are all independent, so I can just work and then put together, merge together. And of course, it's quite easy to implement, because I just be able to sample from some distribution, and computers today are able to sample from a lot of distributions with just one command, one line. But here there are also a lot of concepts, because there is the so-called curse of dimensionality. What is this? The first day someone talks about that, I don't remember who. But it's the fact that the variance of the weight increase exponentially with the dimension of the space where random variables live. And this means that if we increase the dimension, we are in a more bad situation than with the lower dimensions. So it's better to work in smaller dimensions with important sampling instead of higher dimensions. And it's a simple algebra to look at that.
Why is it exponentially?
Just for example, if you work in a space that is the product of m at the power of n, just the variance that you have in one dimension, so you multiply the variances and you get the variance at the power of n. Okay. And of course, also here I'm wondering that in each one of the dimension we have the same measure, so m to the power of n. But sometimes you can work, for example, in one dimension with the Lebesgue measure, in the other dimension with the counting measure. So this is the worst case, of course. Yeah. And you can lower bound with e to the power of or something similar, I don't remember. And of course we have independent samples, so it means that if we sample from, if we are taking a good sample, like that one, that has a high weight, it's not mandatory that the next one will be a sample with a high weight because of this independence. So samples that are from one to another, we are not sure that the next one will be good, will be good enough. And of course, there is also a strong dependence on the choice of the measure m, because I said that if m is too different from p, it's a problem. And now I think that okay. Now we are looking at maybe. Problem, but I just say we are not looking at the importance distribution because of the. I can look at there, but not there. Trust me. We have a problem where P is the sum of two Gaussians. Very easy, but we are not currently able to sample from this sum, because you cannot sample from one, from the other, and then sum together, because of the distribution of the two is the convolution of the densities. So I'm lazy, I don't want to take the a paper and write down the convolution of the two, and so I introduce an importance density that is just a Gaussian with zero mean and some variance, and I take samples from that. I take a lot of samples, 1,000. Okay, which is the problem? Is that if I take the variance of the importance distribution too small, and here you have to think something like that, okay? Like, who was it? Disney, Immagina poi, no? Vabbè, don't care about that. So if I take the variance, no, but probabile, probably, I don't know.
We trust you.
Okay. If we took the variance too small, then we are not able to sample, for example, something like here, because the majority of the samples would be close to the high peak of the importance distribution. And this is why I get an histogram that it's terrible. We see also here that there is a little guy that went in a high probability region for P. And it has a high weight, but the majority of the samples are in the low probability region for P. Okay. This is the one with a too big importance distribution, so it's quite flat. The variance is huge, maybe 20 or something like that. And histograms shows that the majority of the samples are far from the high probability region for P. And I just cut the histograms, but in order to have the same scale. But there are a lot of samples far from here. And this is why the beams are so huge, the basis of the histograms. And here it's a good choice for the importance distribution, and we see that we can reconstruct the whole posterior. Okay. And of course here I just painted out again, we just saw that in the previous presentation, the fact that the weight of the sample, where here we have a marker size that is proportional to the weight, is nothing but the ratio between P of x and M of x, because here we cannot see it, but something like that.
Could you elaborate more on the weight W in this exact case? So we know P and M. How can you compute W without computing P?
I don't know, but I compute P because I'm able to evaluate that in some points. Okay, I'm able to evaluate P, but I'm not able to sample from that. Why? Because if I want to evaluate P, I just take, for example, 0. I evaluate a Gaussian distribution in 0, centered in 2 with some mean, and then I sum another Gaussian centered in 0, another Gaussian evaluated in 0, centered in -2, and with some variance.
So that is not the density of the sum.
No, but ok, facciamo così. If you have a signal, okay, just imagine that each one of these distribution is some signal that comes from the Earth, and then you have the superposition of the two signals. Okay.
Yes.
But if you are able, you measure it, so you have the forward problem. Okay, you are able to evaluate at each time how what is the value of P. The problem is not evaluating P at each time. The problem is that I'm not able to sample from it, so I'm not able to have histograms that are distributed in that way. Why? Because if I sample from the first one, and I'm able to do it with a PC, then I sample from the second one, and I just sum the samples. Okay, so I put them together. What I get is a Gaussian distribution centered in 0. Yes. I don't get this distribution, even if I'm able to sample from both one.
So that distribution is just the sum of the densities?
Yeah, the distribution is the sum of the densities.
It's not the sum of the
okay.
variables. I think that's the point.
Yeah. Okay, I thought it was a sum of two random variables.
Ah,
and
no,
that
no,
was the
no,
opposite.
no.
You,
Okay,
you,
yeah.
You know how to sample, but not the density.
Okay,
Instead,
yes.
you know the sum of the density, but not. You cannot sample.
Yeah. No, okay, you're right. It's wrong to write in that way. I should put here like a convolution product or something like that. Yeah, because the density of the sum is the convolution of the densities. Yes, so I'm able to evaluate at each time, but I'm not able to sample from. And if I'm able to sample from, if I'm able to reconstruct an histogram like that, then I can evaluate the mean, the variance. I'm able to see that there are two peaks. So our interest is, for example, the mean. I know that there are two means, so there are two Gaussians with such mean, etc., etc. Of course, this is a toy example where I know everything. You just think that sometimes you don't know the mean and you want to find them. Okay, so you propose at each time, but this is Markov chain, and we will see it in a little bit. See? In the middle example, I don't remember. Maybe it's always a Gaussian with 0 mean and some variance, but the variance is 2, I think. The first one is 1. Sorry, just say it in one moment. The first one is about 0.5, the second one is 2, and the last one is 10, not 20, sorry. Yeah, I just... the best one. What is this? Can I go on, or...? Okay. What is this? This is a plot where we see the standard deviation of the importance density. So how peaked is the Gaussian where we are sampling from, and here we see the effective sample size. And we see that if we use it too small, it means that a lot of samples are in a bad probability region because are here. If we use it too big, also because a lot of samples are outside. And here we see the same plot with the standard deviation for the importance density, and here the variance of the weights. So maybe should be in a log plot, but in order to look better at that, we have a peak where we are using a good choice for the standard deviation, and then we see that the variance of the weight increases when the standard deviation becomes bigger. Okay. Of course, I think that it's more intuitive, this plot, but here we see a little bit a link, a connection between the effective sample size and the variance of the weights, because here the variance of the weights decrease, and roughly about in 2 it starts increasing, because here maybe you don't see it, but it's increasing, while the effective sample size is going down. But also because here the scale is totally different. There are this one destroy the plot. Okay, but for what concerns a Bayesian point of view, we can look at another example where we have a data that is written like that. We know the forward problem, that is a Gaussian distribution. Measured at 1, centered in X with some variance. So our unknown is the mean of the Gaussian. And then we have a prior distribution on the X that is a Gaussian distribution centered in 0. You can read it. And we set just a Gaussian distribution for the noise. And of course, I said that the likelihood, so the distribution of the data given the unknown, is the translation of the distribution of the noise. And now we see that the distribution of the likelihood is the same of the one of the noise, just translated and centered in our current state. See?
I don't understand the f of x equals to...
Okay. Evaluation, mean and variance. This is the density evaluated in 1 with mean x and variance 1. Again. The posterior distribution is this one. So the one we saw before with 2 peaks. One huge peak and the other one that is smaller. And of course this means that there is a high probability that the mean for what we measured is 0. There is a high probability, not so huge, that what we measured has mean 2. So we want to reconstruct the mean for our forward problem. Okay. And we used importance distribution that is that one in blue with a huge variance, with a right variance. I just did the same thing as before and I choose the one that has a high effective sample size. And here we see just how the approximation of the normalizing constant works depending on the number of samples. So here we see the relative error for the normalizing constant and the number of samples. If we use more particles, the error goes down. Not so fast, because I'm using only what I'm explaining you. So I'm not using what is called resampling. But I'm for the ones who knows it, okay, I'm not using resampling. For the others, go on. And this one is the obtained posterior distribution, importing from this importance distribution. I'm able, okay, maybe here it's clear, it's more clear, because I'm able to evaluate f of x at each time. So I'm able to evaluate the likelihood and making the product likelihood times the prior, because I know it, I get P. Because P is the posterior distribution. And the posterior distribution is the likelihood times the prior. So from each x that I take, and I take x from the importance, I take x, I sample x, I evaluate the f of x, so I'm able to evaluate the likelihood, then I just multiply the prior, I know it is a Gaussian, is a normal distribution, and then I get the P, the distribution of the posterior. C.
So you said before that you don't even have to be able to compute the normalizing constant, right?
Yeah,
So you don't have to calculate the integral?
No. I don't have to calculate the integral. Here I just plotted this in order to show that the normalizing constant is quite well estimated by the algorithm.
Okay.
The relative error is quite big. It's 0.05%. So in the better case, but I also said that this is just an example. Nothing is performs at best.
No, okay, because I was thinking when you compute the ratio between the density and the density of your distribution, the one you sample from. So if you don't know the normalizing constant,
I don't care about that. I use the unnormalized weight. So I just, for example, if the integral sums to 3, I don't care about that. I don't know it. I don't know the normalizing constant.
Okay.
I just evaluate it, and then and then I normalize the weights.
Okay.
I make sure that the weight sums to 1. So I just take the weight and divide it by the sum of all other weights.
And is it still unbiased?
No, it's asymptotically unbiased.
Okay. So you lose that property when you do
Yes.
discrete. Okay.
Yeah. This is not unbiased anymore, but asymptotically see if yes, if you do the limit. Okay, and that one is the obtained posterior distribution, as we said. Okay, Markov chain Monte Carlo. What we want to do is learning from the past, but because I said before that with important sampling, I sample something, and I'm not sure that the next one will be in a high probability region. So I want to learn from the past. But if I learn from the past, I don't have the property of independence between the samples. So I don't have the strong law of large numbers. But I can use a Markov chain. And if I use properly Markov chain, I still have the advantages of strong law of large numbers, the so-called Ergodic Theorems. And here we see the evolution of a chain, but later we will see it again. Okay, so the philosophy is that there is one sample that moves and explores the space, and using some path. And we have to set a properly path in order to guarantee the ergodic theorem. I hope that you know a little bit about Markov chains. We have at first to specify what a transition kernel is. Transition kernel are functions that tells us the probability of a move between the point X and a region A. So a transition kernel can be seen as the probability of being in X and moving in the region A. And we have two properties. This has to be a function in the first variable and a measure in a measure in the first variable and a measurable function in the second variable. So if we define a transition kernel, we can say what a Markov chain is. Markov chain is a sequence of random variable is a Markov chain if the distribution of these random variables is given by an initial distribution, P0. So we say how the system is at start, and then through the kernels we evolve the system, and so we have some dynamics. We can see it like in that way. So we start with a configuration and we evolve using these transition kernels. The transition kernels are nothing but the conditional distributions. Okay, but in a more general state, these are called the transition kernels. Of course, here we see Markov chain called time homogeneous, because the transition kernel doesn't depend on the instant. So we evolve always with the same distribution. We evolve always with the same pattern. Okay. I said that we have to introduce some information, some definitions on the chains, on the property of the chain. And the first one is the so-called invariance. A chain is invariant with respect to a measure if, when we evolve through K, so we start with P and we evolve using the transition kernel, we are still distributed as before. So a chain is invariant if the kernel doesn't change the distribution. Of course, this is useful because I recall you that we want to sample for using a kernel, so we want to evolve, but we want to be distributed as P. So I want to be distributed as P, sampling using a kernel, so moving using this kernel, but then I would like to be distributed again as P. I don't want to change my distribution. The problem is that this property is difficult to be proven. And this is why we use often the so-called detailed balance condition. This is a condition that says if we are in X and we move in X prime, this is the same of the reverse move. So being in X and moving in X prime is the same as being in X prime, this is a typo, and moving in X. So we can go forward and back. Okay, so the idea is to build a Markov chain with an invariant distribution that is our target distribution, and evolve using the transition kernel. And of course, we enforce the invariance using the easier detailed balance condition. And the invariance, I recall you, that is the one that ensures this. If we are distributed as P, the next one will be again distributed as. The problem is that if the initial distribution of the chain is different from P, then it should be is not mandatory that we can reach P. So we start with an initial configuration, and then we want that the kernel modifies this distribution into the target distribution. And then we don't have still the convergence theorems, and we don't really know how to build that chain, because it's a problem. We don't know how to build it. Okay. Of course, we are using kernels that moves only with one step, because we are moving from xn to xn plus 1, or xx prime. But we can also move with multiple steps. So here we are define what is called a multiple step transition kernel that tells us the probability of being in x, n, and moving in xn plus k in k steps. And is nothing but the superposition of all possible paths that goes from xn to xn plus k. Okay, it's very simple. I just take the all possible paths and then I sum the probability. And this tells us the probability of moving from xn to xn plus k. Okay, next step. Okay, this is k. I have to change the picture. You cannot see it, so. See?
Why there is an integral and not just sum?
Because you have this. Sorry, one moment. Yeah, because you have to remove the dependence on the all other variables. You want to move from xn to xn plus m. Okay. If you don't integrate here, this is a continuous case, so we are living in a continuous world. And here you have the dependence of x0, xn. Yeah, this is var. Xn, xn plus 1, xn plus 2, xn plus 3, etc., etc., till xn plus m. then you have to marginalize with respect to the first two variables, and so you eliminate them, integrating out. This can be seen as a sum if the kernel has a density with respect to the countable measure. Of course, here you sum in this picture because there are some points. But I'm writing down something that is more general and still works with the Lebesgue measure or other stuff. Okay. So, invariance, I don't change the distribution using K. Detailed balance condition, an easier way in order to get invariance. Then we have to introduce two different definitions. The first one is the irreducibility. Don't look at that, the definition, okay, it's great, just read it if you want, but the fact is that a chain is irreducible if we can reach each set starting from everywhere. So there are, I can visit the whole possible region of the space. And this means that the chain is irreducible. And then there is another property useful for the convergence theorem, that is the so-called aperiodicity. Aperiodicity, it means that there are no certain path, there are nothing is predictable, so there cannot be the fact that I start from somewhere and then I certainly goes in another place. So starting from a point, I can reach each other points, and so everything is stochastic. Everything is not deterministic. So there are no deterministic paths. Okay, this one sounds good. Okay, this one is the aperiodicity. Okay, with so a little recap. We want to have the invariance, so if we use K, we don't change the measure. We start with P0, that sometimes is different from P. So we want to reach P using our kernel. And how can we reach it? How can we define something that says, oh, in the limit you arrive at P, our target distribution, with the limit low. So we say that a measure is at limit low for our chain if in total variation, after some iterations, so after a huge enough number of iterations, this is another type, or this is M, this is the multiple step kernel. So if I use a lot of steps, then measuring with the chain and measuring with F is the same. So I start with P0, I hope that the limit low exists, and I hope that the limit low is B, and then I'm able to reach it. So after a large enough number of samples, I can reach the limit low. So,
Excuse me?
see.
Why the total variation is just a definition?
Yeah, this is just a definition.
Okay.
I think that maybe one can use a different measure, but I think that the main focus is that theorem that says that if I have an irreducible and invariant, or that satisfies the detailed balance condition, then there exists only one limit low, and the limit low is the measure that is irreducible with respect to K. And this theorem holds if I use that definition for limit low.
Okay.
I think that the order is different in history. They discovered that with these conditions, that holds, and then you say that the limit low is defined as in such a way.
So it works only with the strong conversion.
Yeah. But it's not terrible, because irreducible, it means that just think about Gaussians. You have to choose a Gaussian that has a large enough variance in order to move everywhere. So if we have two sets that are separate, I have to choose a variance large enough in order to move from a place to another. It's not a restrictive condition. You have just to fix it. Okay, so with these informations, we are able to write down the ergodic theorems, and I hope that you can distinguish between the two colors. The first one, I don't write down, read the hypothesis. If you want, just do it. The first one is the strong law over large numbers. So even if we are using a Markov sequence, a Markov chain, there is no independence, then we can reach almost surely our integral, and then we also have the convergence in law, so the central limit theorem. Green one, strong law; blue one, central limit. See?
The hypothesis of invariance. Where is
Invariance. I write down detailed balance condition because we know we don't prove the invariance, we always prove the detailed balance condition. So it's easier for people that are looking at that read the detailed balance condition.
I don't understand a very simple thing. If there is invariance, you can, and you start with P0, then you obtain always P0. How
Yeah.
do you reach P?
Good question. Invariance with respect to something. I'm invariant. I'm not invariant. A measure is a kernel is invariant. I would like that the kernel is invariant with respect to P. This means I start with P0. The chain is not invariant with respect to P0. So if I use K, P0 changes again. And if I have the limit law, and the limit law is P, every time I use K, I get closer and closer to P. And if it is invariant, once I've reached P, I don't move. So this is the path. Okay, and of course, this is the classic central limit theorem with independent random variables. These are not independent. In fact, sometimes this is not called central limit theorem, but this is the central limit theorem for Markov chains, because due to the fact that there is this term that depends on the correlation between the random variables. No? It's okay. Okay, and now, okay. This is the what I've said.
Okay.
So I can skip it. And so now we have to choose how to build that chain. And how can we build it? There is a. Could I skip the slide? Yeah. Okay. How can we do it? There is an algorithm called the Metropolis Hastings that is based on the fact that we use a mechanism of accept and reject the proposal. So we propose a move, and then we see if it is good enough. If yes, then we move, so the chain moves. If not, we stay again where we were. How can we build that kernel? The kernel for the Markov chain, we use a proposal kernel where we're supposed to be able to sample from. Again, it looks like M, but it's not the M of important sampling. And then with some probability, we accept the proposal. So we sample from K tilde. With some probability, we accept this movement. Otherwise, we stay where we are. We stay where we are with a probability 1 minus alpha. Okay. So we propose, with probability alpha we accept, otherwise we don't move, so we reject the proposal. The fact is that we don't really, we don't need to evaluate this integral. We just evaluate alpha, otherwise we stay where we are. Okay, so this part is not our interest. Okay. And of course, the choice of alpha defines the chain properties. because it's the probability of accepting or rejecting this. And now, how can we choose alpha? We are free? No, because we need that this k is invariant, so the detailed balance condition holds. And if we write down the detailed balance condition for k, it means, of course, the same for k tilde, because if we stay where we are, it's easy to say that the two parts of the equality are equal, because xx prime is the same point if we don't move. If we move, we use k tilde, and then this means that alpha is nothing but alpha times this ratio. And the ratio is, again, repeated, we are in x prime and we move from x prime to x, and we are in x and we move from x to x prime. So always the double face. There are a lot of choices. Because this means also only that alpha should be less or equal than this ratio. Alpha is a probability, so it's less or equal than 1. And so we can say that this is less or equal than of this ratio. Metropolis Hastings choice is the optimal one, saying that we imagine that this alpha is 1. This is less or equal than 1. We take the biggest one. Okay. So the Metropolis Hastings choice is the minimum between 1 and the fact that we move from x prime to x or otherwise. In the simpler case where k tilde is symmetric, so we can simplify this expression, they die. It means that alpha is nothing but the ratio between the values in the proposed point x prime and the actual point x. If we are proposing, maybe, no. Okay, this one is better. If we propose a point, next step, that has a higher value for p, then we move, because we are going better and better. Otherwise, we reject with probability 1 minus alpha. But it's not mandatory that we reject. If we propose a point that is worse than the previous one, sometimes we move. And you maybe can say, why? Just suppose, we are here, we start moving. If we reject when we are proposing a step that is worse than the previous one, once we reach the maximum, we don't move, so we cannot see the other peak of the distribution. If otherwise we can move, even if the proposal move is worse than the previous one, then it means that we can find also another part of the distribution. So we explore better the space. And here, why do we use Metropolis Hastings? Because I said that this one is less or equal than this ratio, and this one is the choice of Metropolis Hastings. There are some other choices, but the convergence is faster if we accept as much as possible. So if we move a lot, we converge faster. And so this is the optimal choice. In fact, everyone, I think, that use Metropolis Hastings when they use Markov chain Monte Carlo in that way with the accept and reject scheme. The alpha is the better for Metropolis Hastings. Okay. Okay, no. Okay. Sorry for the time. The pro and cons for the Markov chain Monte Carlo Metropolis Hastings. Here we see that we can move in this little video even across the two peaks because we choose a large enough proposal kernel that moves at each time. Okay, so we learn from the previous step because of the Markov chain property. We don't get stuck in a local maximum thanks to the the fact that the chain should be irreducible, so we can reach every point of the space starting from everywhere, and it's quite easy to implement because we just have to evaluate this alpha, so the probability of the move. Of course, it's not parallelizable because the actual step depends on the previous one, and of course it depends on the choice of the proposal kernel, because if I propose always a move that is terrible, I cannot explore properly the space. And there is also a problem that depends on where we start. It's true that the irreducibility allows us to reach every point of the space starting from everywhere. But of course, we use a fixed number of iterations. If, like here, we start too far from the high probability regions for P, we lose a lot of time moving and for reaching the high probability region for P. And this means that, for example, if here I evaluate the total variation distance between that distribution and the P that I want to evaluate, these are different because I've not used a large enough number of steps in order to being closer to the limit law. So the number of steps that I have to use in order to reach the limit law also depends on the initial point. Otherwise, if I start, for example, here I started in 0, okay, you say you're lying, yeah, you're cheating. I start from 0 and I can use the all samples, the all moves in order to approximate the posterior distribution. Here I started in minus 15 and I spent a lot of time for reaching the high probability region. And this is called burn-in. What people practically do is I do 1,000 steps, then I stop, I trash the old stuff I've done till now, and I start again. So I start from a point that I'm sure is closer to high probability region of See.
Do you know if it's possible to quantify the speed of convergence of the distribution?
The theory says that it converges as all Monte Carlo algorithms because of the Ergodic Theorem. In practice, no, it's slower because also that depends on where you start. In fact, the order of convergence depends also, I don't remember, sorry, but depends also on the choice of alpha. Because here where I wrote somewhere here, okay, that the convergence is faster if we accept as much as possible. I think that it's called Perksum choice, Perksum chain. I don't remember the name properly, but they prove that if you accept more, the more you accept, the better, the faster you converge. But I don't remember the differences.
Okay. So it also depends on the kernel?
Yes,
right?
yes. Just think that if if you do little steps, you wait a lot of time in order to move. If you do big steps, you can move here in only one jump. So there are a lot of variables for the problem, and everything incides on the speed of convergence. But I don't remember really the most important one. If it's more important the acceptance rate or the variance for how much do you jump.
Okay.
Okay, here we see again the same problem as before, written again in the worst way, because of the copy and paste. We used a proposal kernel that is a Gaussian that moves differently from before in importance sampling, where we used only one Gaussian and we take the whole stuff from that Gaussian. Now we have a Gaussian that is centered in the actual point. So now I'm centered here, I take one sample, then I move, and so on. So this Gaussian moves and is centered in the current state. And of course, here we see the percentile of the rejected proposed value depending on the standard deviation of the proposal. So it's something similar like the ESS. Because if you use huge jumps, then it's probably you will reject the proposal move, because it's too far from the high probability region. Otherwise, if you do 2 small steps, it's probably you will accept more, but you will also move. You don't have so much big jumps. So, okay, a good percentile is 0.2. So I choose 1. It's roughly 1. A good choice for the percentile of the rejected proposals. And so the 20% of the time we reject, and the otherwise we accept. And okay, I think that you can read this. And what? Okay, this one I just said, and this is the result. It's very simple. Nothing useful. And again, the same problem for the Bayesian approach. This is the same. And again, I use a normal distribution centered in the actual point with one bias. Okay, sequential Monte Carlo in 2 minutes. Only because I would like to show you that picture. Because we want to merge Metropolis, Hastings, and importance sampling in order to approximate a sequence of distributions that becomes more and more complex. So we start with a distribution that is so simple, then we modify it in order to reach the target distribution. And we practice something like, I practice a step of Metropolis Hastings, so I evolve the particles, I mutate the particles, I select the particles, so I use the same words over here, using Metropolis Hastings, and then I import that particles from the actual distribution that is PT to PT plus 1, using importance sampling. This is the idea. For the ones of you that were here during my presentation, I've just said that. So we explore more and more complex spaces. We are giving more and more information at each time, and of course this can be useful in situations where our system evolves in time, because of each time we have a new information, we modify the actual distribution. Okay, so what we are doing is a change of measure, a measure for a Markov process. We start at time t minus 1. We are in the actual state. Then what I've said that we evolve using a Metropolis Hastings step. So we use a kernel of Metropolis Hastings. We evolve the particles, and then we import that particles into the next distribution. So we weight that particle. Of course, sometimes we don't have the normalizing constant, so we add the normalizing constant. Okay? Here, it's clear what I've said, that SMC works in increasing dimensional space, because here we have the dependence on t minus 1 and t. To the fact that we want to approximate the actual distribution at time t only with the xt, then we marginalize with respect to xt minus 1. because this notation is terrible. Yeah, how can I say that I'm integrating in xt minus 1? And of course, the weights are the ratio between pt and pt minus 1, because we are importing in such a way. Okay, you cannot see here a little movie, but there is, trust me, there is a distribution that starts with a Gaussian distribution and then modifies into the posterior one. This is the same posterior that we saw in the previous example. And the most common sequence used for importance sampling, not most common, but it's widely used, is the so-called tempering sequence. We start from a distribution that is that dominates our target distribution, and we use the Radon-Nicotine derivative for as a weight that starts. So we start from mu, that is the initial distribution, a single one. Then we give more and more weight to the density, to the Radon-Nicotine derivative, and we get the target distribution. I think that this one is more clear in the Bayesian case, where we start with the prior distribution. We use the likelihood density. This is a density because for the Bias Theorem we the hypothesis is that the likelihood admits density with respect to the prior. So we have here the likelihood, and we give more and more weight to the likelihood. So we are passing from the prior to the posterior using the likelihood. What does it mean? We start in a model where we know only what we think to know about the unknown, and then we give the information coming from the data, because the likelihood gives us the information of such configuration given the measured data, and we weight these informations more and more. Niente. You can see it. And here you can see that the approximation of the posterior distribution at time t, and then maybe now you can see that the distribution become more and more peaked. We have to wait. Okay, it's becoming more and more peaked because we are giving the informations coming from the data, and also the histograms become they adapt because we are importing into the next distribution. Okay. Conclusions. Thank you for the attention. Okay.
Thank you very much for the talk. Also, some of you already asked questions during the talk. Do we still have some more questions to the speaker? Yes.
Please.
About Markov chain Monte Carlo, and in particular about the kernel. So, if I understood well, the choice of alpha makes the choice of the kernel not important. I mean, I can choose whatever k, and then alpha makes it invariant with respect to p.
Yes, because okay.
That is
well, you're right, but the answer is no, because this is a brainstorming. If you choose a kernel that is very, very peaked, and you have two regions that are not connected, okay? So you have regions that are not connected, and you choose a Gaussian distribution, very, very peaked, and you start from the laser here, you cannot move into the USB. Okay? Okay, yes. Terrible. The choices of alpha tells us that the kernel is invariant because of the detailed balance condition. Doesn't tells us that the chain is irreducible. Okay, so we also have to check that we can move and explore properly the space. The choices of alpha makes useless the definition of K for what concerns the invariance. So if we reach P and we use that alpha, whatever is K tilde, that is K. If I choose alpha and K tilde, then it's K. When I reach P, I don't move anymore. But K tilde has to be chosen in such a way that we can reach every point of the space. Because we need for the somewhere here, the irreducibility.
Okay, so Gaussian random variables are, or Gaussian distributions as the kernel choice are always good because they have an infinite support.
The fact is that also, for example, if you want to move, here there was an example, but we don't care about that. If you want to move from spaces, for example, of different dimensions, so like here, we have we are in a point x that is 1 mean, and I propose, for example, oh no, in my opinion, the signal is composed by the superposition of 2 Gaussians. So I add another mean because I think that there are 2 Gaussians. Then here maybe I don't use a Gaussian distribution for importing that. Why? Because at first I have to choose the number, and the number I cannot extract the number of Gaussians from a Gaussian distribution. Why? Because I need, for example, a Poisson, a discrete distribution for the numbers. Maybe I'm not explaining. No. So, for example, if your variable is a number of stuff, of something, then the kernel is not properly if you use a Gaussian, because the majority of the time you will extract a real number.
Yes.
Okay.
But what I wanted to ask, in the example at the end, so you used K as a Gaussian.
Yeah.
So you need,
it's a simple one.
you don't need to check that that kernel is invariant.
Yeah.
Because alpha is chosen as.
No, invariant. No, I have to check that it is reversible,
But
so
it's a
that
Gaussian,
I can
so it
move
is.
between these 2 peaks. But I don't have to check the reversibility.
Thank you.
And yeah, you are.
Any other questions?
I was just curious about the value 0.2 for the acceptance rate.
Why? Yeah, it's heuristic. I don't really know why, but in literature you find that this is a good value. Maybe because it means that you accept a lot, because you accept the 80% of the time, so the chain moves and you reach faster the limit low, but you don't accept the trash. Maybe it's something like that. You don't want to accept terrible choices, but you just accept the majority of the time.
Any other questions? I have a last one. Could you go to slide 27? Perhaps it's just a misunderstanding of my probability knowledge and all the limits.
Okay, here.
Oh no, next one. 27.
Sorry.
You said that on this slide, like colloquially spoken, every time we use the K, we get closer in the limit. Yeah, but
Yeah.
it's not monotone. Or do we have monotonicity? Like those almost everywhere?
No,
it's just like.
Yeah. It was just for roughly speaking,
Okay.
that we are
No, I
converging.
totally understand.
Yeah.
I totally understand, but I was like, perhaps I don't understand. Yeah, but I guessed you wanted to say
Okay,
it.
no.
Okay. So
It's
because
not monotonical convergence. It's
okay.
just
That was
almost
my
sure
question.
and low. Okay,
So we thank the speaker again.